All right, welcome to the deep dive. Today we're going to take a close look at solar photovoltaics, or PV for short, as it's often called. Our listeners have told us that they really want to grasp this big picture of solar without getting bogged down in all the, really technical details. So consider this like your express lane to understanding how sunlight is quickly becoming a major player, maybe even the dominant player in the global energy system.
Absolutely. And, this is not something that's like way off in the future. It's happening right now.
Right.
Today, we're going to use this paper, Solar Photovoltaics and 100% Renewable Energy Systems, to really give you that clear path to seeing how solar PV has gone from something that was pretty niche to potentially being, the king of the entire energy market. So what we're going to do is try to pull out the most important insights about solar's history, where it stands today, and, really try to project where it could go, especially if we're serious about a future where the world is powered by clean energy.
Okay, so let's unpack this a bit. This paper, it starts off with a pretty bold statement right off the bat, basically saying that since the 1950s, solar PV has had the strongest long-term growth of any energy technology out there.
Yeah.
And we're not just talking about like steady growth. It's being called the king of energy markets and the cheapest way to generate electricity in many places.
In many places, yeah. And that's really the big takeaway here, right? The implication is that if you take solar PV and you combine it with some other, really smart technologies, things like batteries to store all that energy and electrolyzers to make clean fuels, which we'll talk more about later on. It makes it totally plausible that solar could become the primary source of energy.
Wow.
Within just a few decades.
Wow.
Not just powering your lights, but everything, like fueling the entire global economy.
Yeah, and that idea of a 100% renewable energy system, with PV playing a starring role, really seems to have taken off the research community since the mid-2000s, right? Like, more and more experts are recognizing how crucial solar is.
Absolutely. It's like that true potential of solar to completely reshape how we think about energy has really come into focus with that recent research. The data, the projections, the real-world numbers are pointing to this solar age that's critical for our planet.
Now, let's rewind a bit and talk about the history.
Okay.
The photoelectric effect, which is like the fundamental science behind how PV works, was discovered way back in 1839 by a guy named Becquerel.
Yeah.
And then Einstein, of course, explained it like super clearly in 1905, which won him a Nobel Prize, of course. But, it took quite a while for that science to actually turn into something practical, right?
Okay. Well, right. And it's interesting how those really early, almost lab experiments led to some niche uses in the late 19th and early 20th centuries.
Yeah.
But the real beginning of modern solar PV, like the stuff we see today, really started with this crystalline silicon stuff at Bell Labs in 1941.
Okay.
And that was actually kept secret until 1954. And even then, the efficiency, like how much of that sunlight they could convert into electricity, was only around 6%.
6%? That seems so low compared to today's technology.
Right. It's tiny.
But even then, solar PV, it had this knack for becoming dominant really fast in new markets. The paper talks about how it was the top power source for those space satellites in the 50s and 60s.
Right.
So even with those humble beginnings, I think the key insight is that solar found its niche.
Yeah.
Where it was just better, despite any limitations.
Yeah.
We see that pattern repeating.
And since then, it's just been this constant evolution. Scientists and engineers are always messing with new materials to capture that sunlight and make it into electricity.
Right.
And they've been pushing the limits of, how efficient that conversion can be, both in labs and then, the products you can actually buy.
And of course, with all that progress, the costs have been dropping steadily. The paper mentions they've been tracking these costs since, like, the mid-50s. And the first analysis that really look at this decline, like in terms of learning rates, so how much the cost goes down every time you double production.
Right.
That was back in 72. A researcher named Wolf found a learning rate of 21 to 31% just at the level of the individual solar cells.
Yeah, that was a good start.
Okay.
But it was really Swanson in 2006 that got everyone's attention.
Yeah.
He looked at whole modules, like the panels on rooftops from the late 70s to the early 2000s. And he found a 20% learning rate. And that number really stuck with people in the industry and just in general. And what that means is that every time production doubled, the price went down by 20%.
Right.
And that's just, a huge force-driving change.
Okay, so this cost is going down predictably every time we make more.
Basically, yeah. And it gets even more interesting. So Kirsten and some other folks did even deeper research and found that learning rate, that 20%, it was pretty stable for over 50 years. From the mid-50s to the late 2000s. But of course, there were ups and downs in that time.
Right.
But then the 2010s hit.
Okay.
And that's when things really changed. The learning rate for those modules jumped up to a crazy 40%.
Wow.
Which puts it right up there with other silicon-based semiconductor tech, like the chips in your phone or computer. And what drove that, it was this combination of factors. Huge increase in production, like mass production, more standardization of the modules, fierce competition between all the companies making them, like super fast innovation, much easier access to investment money, and obviously this huge demand.
Right.
A lot of this was pointed out even earlier by a researcher named Nemeth.
Okay, so this cost is dropping consistently. Who are the early pioneers, like the ones who really pushed this technology forward and got us started on this path of cost reduction?
Well, the initial push for all this, the early research, creating those first markets, like you mentioned with the satellites, and figuring out how to actually mass produce these things, that was really led by the U.S., Japan, Germany, and now, of course, China is a major player.
Okay, so that consistent drop in cost is really powerful.
Yeah.
But where has all this led? The paper has this figure 1, which is like a graph showing this huge upward climb of market growth, especially recently, like year over year.
Yeah, it's been incredible.
And this isn't just random. There are key innovations driving this.
Yeah.
The paper points to 4 of them. First, there's the original crystalline silicon solar cell. Second is the development of those tough PV modules, the panels that can handle being outside here on Earth.
Right.
Third is those rooftop solar programs that made it easier for regular people to get in on this. And then fourth is the rise of those huge utility-scale solar power plants, those massive solar farms.
Yeah, exactly.
What's important to understand is that each of these innovations, they kind of unlocked new markets, right?
Exactly. It was a sequence.
Like a chain reaction.
Yeah. First, it was powering those satellites, then bringing electricity to remote places, then connecting to the grid with rooftops, and now it's these giant solar farms.
Okay.
And the paper says the next big one is going to be power to X.
Power to X, right, which we touched on before.
Yeah, using that cheap electricity from solar to make, like, e-fuels for plane or e-chemicals for industry.
It's wild to think how big some of these solar projects are now. They list the 5 largest PV plants in the world.
Yeah.
All over a gigawatt in capacity.
Yeah, that's huge.
Like places like Badla and Hwanghae, over 2.2 GW, Pavagata over 2. Benban and Tanger are massive too.
Yeah.
And in total, there are 9 plants over that 1 GW mark, spread across like the UAE, India, China. The scale is mind-blowing. Like the same technology can power a tiny satellite or a whole city. That scalability, I think, is key to understanding how it could become so dominant.
Yeah, and that's one of the amazing things about PV. It's scale invariant.
Right.
You can have a tiny panel for your garden light or a multi-gigawatt farm feeding a city.
Right.
And the basic tech is the same. And the paper also points to the compound annual growth rates.
Right.
Like over 40% in the 2000s, and even in the 2010s, it was still above 20%. You mentioned CGR earlier. That's compound annual growth rate, right? What does that really tell us here?
It shows how fast the adoption of solar has been increasing year after year.
Right.
And because of that, in 2020, solar actually took the biggest share of all new power generation capacity globally. 42%.
That's huge.
That's massive. And in 2020 alone, we saw like 138.5 GW, maybe even 147 GW of new solar capacity added.
Wow.
Bringing the total to a massive 756 GW.
Yeah, to put that in perspective, like in 2020, 18 countries each installed at least 1 GW of PV. The whole global market only hit 1 GW of annual installations for the first time in 2004. And then, just 3 years later, Germany became the first country to install over 1 GW in just 1 year.
Wow.
The projections for 2021 were even bigger, between 160 and 209 GW, and the global manufacturing capacity for PV was supposed to hit around 400 GW by the end of that year, and there are still huge expansions going on.
So the growth has been, phenomenal,
yeah.
Which makes the next point in the paper even more interesting. They say that most of the market analysts, the energy system researchers, like back in the 2000s, they totally missed this coming solar boom.
Yeah.
They just didn't see it coming.
It's funny how, even though you could kind of see this coming based on those learning rates, almost everyone underestimated it.
Right.
Like, significantly.
Given the incredible growth we've seen, it's pretty shocking they missed it. Like, What happened there?
Well, the European Photovoltaic Industry Association, EPIA, in 2008, they were one of the first to really show the true potential of solar. They said PV could supply 6 to 12% of all electricity demand by 2020.
Okay.
At the time, the EU's solar share was only 0.2%.
Wow, that's a tiny amount.
Tiny.
Wow.
And even researchers who were super optimistic about renewables, they were way off in their projection.
But by the end of 2020, a bunch of European countries actually hit or exceeded those projections that EPIA put out.
Yeah.
Like Germany, Greece, Spain, Netherlands, Italy, Belgium, all with big chunks of their electricity coming from PV. So how did EPIA get it right when so many others got it wrong?
Well, EPIA based their stuff on research done at Qcells, which was like the top PV company in the world back then.
Okay.
And their method was built on the concept of PV grid parity.
Right.
So that's when your home solar panels are actually making cheaper electricity than what you're getting from your utility company.
Right.
They later expanded this to fuel parity, which is when like a big power company realizes it's cheaper to get energy from the sun than from, buying coal or gas.
Yeah.
And that's even before they factor in the cost of actually building the power plant.
So they weren't just looking at like today's costs. They were predicting future costs based on how the market was growing and those learning rates.
Exactly.
That allowed them to like look ahead and see how much PV systems would cost, how much electricity they would generate all the way to 2020.
Right. And they combined these grid parity and fuel parity analyses, publishing some of the really early papers about terawatts of total PV, like trillions of watts.
Wow.
And they predicted a cumulative market of 600 to 1,000 GW by 2020, which, as the paper points out, is remarkably close to the actual 756 GW that was installed.
Right.
And no other long-term projection from back then really nailed it like that.
That's a huge miss for the industry. It really shows how disruptive and how fast solar PV has been moving.
Yeah.
So if those projections were so far off, what are the latest models saying about the future potential for solar?
Well, fast forward to 2019 to 2021, with way better computer models and more real-world data, the picture's totally different. Research suggests that the total installed solar PV capacity could hit around 70 terawatts by 2050. That's 70,000 gigawatts.
Wow.
And that could cover about 70% of humanity's total primary energy demand. That's all the energy we use, not just electricity.
70%. That's a crazy number.
I know, right?
And the paper even suggests that the cost of energy could stay stable.
Yeah.
During this transition to a zero CO2 emission system by the middle of the century. That would be incredible.
It would be unlike anything we've ever seen.
Right.
And there are a few key insights driving this. We're talking about continued low costs for solar PV and big cost reductions for batteries, electrolyzers, and even carbon capture tech that can pull CO2 right out of the air.
Okay, let's talk about those supporting technologies.
Yeah.
They mentioned batteries first. Why are they so important for solar to become dominant?
Well, the sun doesn't shine all the time.
Right.
So to get past a certain amount of renewable electricity, especially in places without a lot of hydropower or other constant sources, you absolutely need energy storage. Batteries have become way more feasible and affordable, especially in places like Europe. And the demand for batteries from electric vehicles, plus more stationary storage systems for homes and businesses, all that's driven prices down a lot.
Okay.
And that's going to continue.
Okay, so we can store solar energy more affordably now.
Yeah.
And what about electrolyzers? They're the second key technology mentioned.
Right.
What's their role in this future with so much solar?
Well, they use electricity to split water into hydrogen and oxygen. This is super important because you can't electrify everything.
Right.
Hydrogen can be a clean energy carrier, and it's also crucial for making stuff in industries that are hard to electrify directly.
Okay.
Things like green steel, ammonia, e-methanol for chemicals,
Okay.
even e-fuels for planes and ships.
So as we said before, Power to X is about making other useful things from that cheap solar electricity.
Exactly.
So the core of a future sustainable system is this combo of 4 technologies. Solar PV for the cheap electricity, batteries to even out the ups and downs of solar, electrolyzers to turn that electricity into fuels and chemicals, and direct air capture to clean up whatever emissions are left and maybe even reverse climate change.
That's the idea.
And it's all driven by the dropping cost of solar electricity.
Right.
It just becomes the cheapest, most attractive option.
Exactly.
The paper also mentions energy system models, the tools researchers use to make those long-term predictions. It sounds like they've gotten a lot more sophisticated.
Oh, absolutely. They can analyze these transitions in much more detail now, considering things like climate targets, what people want, what resources are available, how much energy each sector of the economy needs.
Okay.
They look at hourly data to account for the variability of renewables. They consider regional differences, and they can even model how different energy sectors are connected, like how electricity can make fuels for cars or heat buildings. That's called sector coupling. And there's a big push to make these models transparent so everyone understands how they work and what assumptions they're using.
They mentioned two leading models, PyPSA and the LUT model.
Right.
What makes those stand out?
Well, they're simulating the future energy system.
Right.
PyPSA was really good at analyzing the European system.
Okay.
But the LUT model, that's from Professor Breyer's team in Finland, it's described as global local.
Global local.
Meaning it can look at different scales from the whole planet down to specific areas.
Okay.
It can divide the world into 150 regions.
Wow, so many.
Way more detailed than most models, which usually use like 20 or 30.
That detail is important because solar resources are so different.
Exactly, yeah. And energy demands, other resources, it all varies a lot from place to place.
So it's these better models, like the LUT model, that show how solar PV, with those key technologies we talked about, batteries, electrolyzers, direct air capture, could realistically hit that 70% global primary energy share.
Yeah, exactly. And the paper even gives us some examples of where solar is already making a big difference. As of 2020, places like Tukalo, that's a small group of islands, they were getting 99% of their electricity from solar.
99% from solar.
Yeah. California was almost at 20%. Countries like Honduras, Australia, and even the state of Hawaii, all over 10% solar. These are like early signs of what could be coming to the rest of the world.
So we've covered the history, the tech, the crazy market growth, and the potential. Now let's talk about the specific role that solar PV is expected to play in these scenarios, where the whole world runs on renewable energy. It seems like there are still some disagreements in those projections, maybe even some underestimation still out there.
Right, yeah. So while the research on 100% renewable energy systems has grown a ton, like over 500 peer-reviewed articles on specific systems since the mid-2000s.
Wow, that's a lot.
Yeah. But how much solar PV is supposed to contribute in these scenarios, that varies a lot from study to study.
Right.
The growth rate of published articles in this field, that was 24% between 2010 and 2020, which is huge.
Yeah.
It shows the real surge in research. Some of the top teams doing this work are led by people like Breyer, Lund, Mathieson, Estergaard, Greiner, the DLR, and Jacobson.
Okay.
The models they use most are Energy Plan and the LUT model.
So all this research is really picking up steam?
Yeah, definitely. It's interesting. The very first global analysis for 100% renewable energy was way back in 96 by Sørensen.
Okay.
But it took over 15 years for the next one to come along. That was by Jacobson and DeLucci. And that one really became a landmark. It's the most cited in the field, and it really kicked off a lot more research.
So they were like the trailblazers.
Yeah, in a way.
Since then, there have been big improvements in how they do these models. Things like analyzing multiple regions that are connected.
Right.
Using hourly weather data to see how solar and wind fluctuate.
Yeah.
Figuring out the best balance between different renewables.
Right.
And this modern idea of sector coupling.
Sector coupling, right.
Which is connecting different parts of the economy with electricity and power to X.
Exactly.
That's all been huge progress.
Yeah, and the work by Bogdanov and Breyer, where they combine high geographic detail with that hourly modeling and power to X, that's been really influential.
Okay.
And then, people like Teskey and institutions like the DLR working with groups like Greenpeace, that's been super important in getting those insights out to policymakers and the public.
Okay, so what about the actual projections for how much solar will contribute in these 100% renewable scenarios?
Right.
The paper mentions they looked at 16 global scenarios.
Yeah.
What did they find?
Well, one of the most interesting things is just how much the projections for PV electricity generation vary between those studies.
Okay.
Some scenarios say solar will contribute a moderate amount, while others, especially those by folks like Persiamo and Bogdanov, see solar PV generating a huge share of the world's electricity by 2050.
Okay.
Like upwards of 93,000 to 104,000 terawatt hours.
Those are big numbers.
Huge. And the studies that predict the most solar also tend to be the ones using the lowest cost projections for 2050. Bogdanov's work is also notable because it's the only one that really looks at using single-axis tracking for those big utility-scale PV systems, which is something we're seeing more and more of in the real world.
Right, right.
But even their cost assumptions might be about 30% higher than the latest projections. So if those scenarios were updated, we might see even more solar dominance.
So even the most optimistic projections might not be optimistic enough.
Yeah, maybe.
It's amazing that even back in 1996, Sorensen predicted a 28% share for solar in total primary energy.
Uh-huh.
But only a couple of recent studies have gone above 40%.
Yeah.
Why are some scenarios still projecting relatively low contributions from solar?
Well, the paper says there are a few key reasons. First, many scenarios, especially those from the early 2010s, just overestimated the cost of solar PV. They didn't see those rapid price drops coming.
Okay.
Second, some rely a lot on bioenergy,
right,
which can be tricky in terms of sustainability, like land use, food production, biodiversity. Third, some models don't really optimize the mix of technologies based on cost. So they might end up picking more expensive options over cheaper solar PV.
Right.
Fourth, some have weird assumptions about how much renewable energy is available, maybe artificially limiting solar.
Okay.
And finally, many just haven't fully embraced power to X and sector coupling.
Okay.
And they often assume costs for batteries and electrolyzers that are higher than what we're seeing now or what we expect in the future.
So it's all about those underlying assumptions.
Yeah.
Especially when it comes to the future cost of solar and the potential of those other technologies.
Right.
It's crucial for getting an accurate picture.
Exactly.
And the paper highlights that we need more research, more comparisons between models to really understand their limits and figure out the most likely paths forward.
Absolutely. You know, as Bogdanov's work showed, the share of solar PV in the electricity supply in a sustainable system, it's usually pretty close to its share in the total primary energy demand.
Okay.
That's because of things like electrifying transportation and heating,
right,
using power to X to make fuels and chemicals, and having strict rules about how much bioenergy we use.
Oh.
The paper even has a table showing countries and regions where PV is projected to provide at least 50% of the electricity by 2050.
Wow.
It's interesting that a lot of countries in the Sun Belt,
right,
with lots of sun, as well as some European countries with interconnected grids, they're expected to reach really high PV shares, sometimes over 90%.
Wow.
That's because they have great solar resources, not as much hydro or sustainable bioenergy, and in some cases, not a lot of wind potential.
So those are the places where solar is really poised to take off.
Yeah. And it's worth noting that the LUT model, the one by Professor Breyer's team, that's used in a lot of these studies showing high PV shares, especially in the Sun Belt and the Global South. That's because it's specifically focused on those regions. It uses strict limits on bioenergy. It incorporates the latest cost data for PV, and it includes things like seawater desalination, which is important for many of those places.
So the model itself is kind of tailored to those regions.
Yeah, kind of.
And even though there are a lot of researchers still doing those simpler greenfield or overnight scenarios, which just imagine a future state without showing how we get there.
The models that do project those high PV shares, like LUT, versions of Osmosis, PyPSA, Energy Pathways, Rio, they have some things in common.
Okay.
They use realistic projections for PV cost declines, and they emphasize connecting different energy sectors through things like batteries and electrolyzers. And we're seeing more studies looking at specific countries showing PV shares above 50%, even in places farther from the equator, which suggests those smaller scale PV systems where people make their own power. And those hybrid systems with PV, batteries, and electrolyzers, they're becoming more and more attractive, even outpacing wind and the need for huge grid upgrades.
So this is painting a picture of a much more solar-powered future.
Definitely.
Which leads us to this critique of how solar PV has been consistently underestimated in those big global energy scenarios.
Right.
Especially from the IEA and the IPCC.
That's a really important point. The paper says they've been criticized a lot for being too conservative in their solar projections.
Okay.
Several studies that came out in early 2021, they looked at the IPCC reports and found they were seriously underestimating future PV deployment. It seems the main reason is that they were using bad cost assumptions for solar PV in those integrated assessment models, or IAMs.
Right.
Like some models were using PV cost numbers that were 4 or 5 times higher than what the industry was projecting and even the actual costs in 2020.
That's a huge difference.
Massive.
So what does this underestimation mean in the big picture?
Well, those who did the critical studies warned that this could slow down the clean energy transition. By making solar look too expensive, these projections could lead to bad policy decisions, money being invested in the wrong places, and a failure to take advantage of solar's potential. They say the IPCC and others need to use a wider variety of models and methods to capture the fast-changing reality of solar.
It's striking when you look at the numbers.
Yeah.
The paper mentions that the average projected contribution of solar to primary energy in 2050 from the IPCC's fifth assessment report and their special report on 1.5 degrees Celsius was super low. Only 3.1% and 6.8%.
Right.
Compared to that first 100% renewable energy paper from 96, which already showed a potential 4 times higher.
Yeah. There's been some progress in newer IAM publications, but they haven't really shifted to consistently using the best and most current cost data.
Oh, right.
Plus, a lot of those models still don't properly include sector coupling, which is key for understanding how solar can decarbonize things like transport and heating, and they often lack a full picture of electrification across the economy.
And they don't talk about 100% renewable scenarios until much later, right?
Yeah. The paper points out that the IPCC only explicitly mentioned those scenarios for the first time in their 2018 report on global warming of 1.5 degrees C.
Okay.
And that was decades after the first research on it came out. They also suggest that IPCC should have more diverse experts involved to make sure those reports reflect the latest knowledge and advancements.
Okay, so this skepticism towards high renewable energy systems, it wasn't just the IEA and IPCC.
Right.
The paper looked at reports from a bunch of other groups, too.
Yeah, and almost all of them from different organizations and think tanks were pretty skeptical about getting energy systems that were mostly or entirely renewable. There were a couple exceptions, though. A report from the German Advisory Council on Global Change back in 2003, that projected a really high 67% primary energy share for solar by 2100. And then there was Shell's Sky scenario. Right. That one came out in 2018. It sees solar having a 32% share and renewables overall reaching 59% by 2070.
That's still not enough to hit those climate targets.
No, not quite.
But it's interesting that it came from a big oil and gas company. Expert speaker.